Hi, I'm Dan Salzberg, and this is an episode of Smart Science. And what prompted this episode, Dr. Andrew Huberman announced on Twitter he's doing a podcast on water. Huberman's one of my favorite podcasters. I really enjoy his cast. I actually saw him live at the Wiltern. It was excellent. And there's about 2,000 questions on here, so I thought what I'd do is go through some of these questions and answer them. A little bit about me. My background is degrees in environmental studies, geography, business administration, and business management. I did a focus on water treatment in my environmental studies program and satellite imagery analysis when I studied geography. I interned for NASA on one of our first global warming studies. I have about 40,000 customers in water treatment through my company, bigbrandwater.com. It runs the gamut from residential customers through bottled water, Fortune 500s, food and beverage, biotech, pharmaceutical, every industry you could imagine. I've treated every kind of water situation possible. So I'll start the podcast by answering a bunch of questions here, and then at the end I'll insert some information from another podcast I did that kind of gives you the fundamentals of water treatment, how membranes work and filters and so on and so forth. Let's go ahead and dig in. So Dr. Huberman, or Andrew, says, what do you want to know about water? The first comment here, is it as contaminated with fluoride as my tin foil hat friends say it is? And Andrew says, unfortunately many regions are. This is a serious problem for people with thyroid issues, but not every region is heavily contaminated with fluoride. I'll cover this in the episode. So the deal with fluoride is it's good for your teeth. A lot of municipalities are putting fluoride in the water because it does help your teeth when you're young and you're growing. It makes your teeth resistant to cavities. There's controversy about whether or not fluoride is healthy for adults, and a lot of people want to remove fluoride from the water. There's three technologies we can use to remove the fluoride. The first being reverse osmosis, which uses a membrane and forces the water through under pressure. Reverse osmosis is going to remove most minerals. Some may be good, some may be bad. The second method is going to be a media called activated alumina, which is a zeolite type media, and I get people that say I don't want it because I hear aluminum's bad. It's an aluminosilicate structure. There's no way for the aluminum to come out in your water. The third method, there's a specific type of carbon that we can use to remove the fluoride. So typically you'll find the municipalities fluoridating between maybe 0.3 and 0.8 ppm parts per million. You also see that as mg/L, which is milligrams per liter. You can kind of use those terms interchangeably. There are very subtle differences, but it's close enough. So 0.3 to 0.8 is typically what you're going to find in your municipal water. The EPA Safe Drinking Water Act says 4 milligrams per liter is the maximum limit. So we'll move on to the next one. Okay, does high pH water actually make a difference in hydration? Is it true you can drink less water if it's higher in pH? Dasani really, the guy's got some negative comments about Dasani. Okay, there's a lot of hype and there's a lot of questions here about water alkalinity, and what I'll say is that there's a whole segment of my industry that we call water quackery, and that's where we have these machines that claim they're going to cure a whole host of diseases from diabetes, heart disease, cancer, and so on and so forth, all through a water system, and none of it's true. At the fundamental level, pH is the ratio of hydronium and hydroxide ions. So a pH of 7 means there's 1 times 10 to the negative 7 moles per liter of H plus is present, and 1 times 10 to the negative 7 of OH minus. So a pH of 6 is going to be 1 times 10 to the negative 6, and then your OH minuses go 1 times 10 to the negative 8. So that's how pH works. To answer the question, does pH of water make a difference in hydration? No. Okay, so your stomach pH is between 1.5 and 3.5. So when you go from neutral, a pH of 7 down to 6, that's 10 times as acidic. Down to 5, it's another 10 times, so it's 100 times. Down to 4 is 1,000 times. Down to 3 is 10,000 times. Down to 2 is 100,000 times. So the pH of your drinking water is going to be totally irrelevant. Okay, I'm looking at the next one here. We have something from Flex. It says explain this, and there's a bottle that says liquid chemtrails contains dihydrogen monoxide, H2O. So a lot of people like to play off of this, all this hype. Chemtrails is a name for these supposed trails coming out of airplanes, which are usually seen over cities more so than rural areas, and what it has to do with airplanes are at a lower altitude. And these supposed chemtrails, 99.9% of the time, it's just strictly water vapor in the plain exhaust. There's no such thing as vapor trails, or chemtrails. It is tap water, and I'm not going to use the expletive. They're from Devon. Is spring water truly the best? Is distilled water okay? Are plastic bottles ruining the water? So tap water actually meets stricter standards than your bottled water. Tap water meets EPA standards, whereas your bottled water meets FDA standards, and there are some differences there. There's all this hype about spring water. Spring water is not inherently any healthier than any other water. So the term spring water just means that the water is coming out of the ground under pressure on its own, versus a well where we're using a pump to pump the water out of the ground. There's no difference. So we could have two wells that are both 500 feet deep. One of the wells is under pressure, so the water comes to the surface on its own, so it's a spring. The other well next to it, 500 feet deep, we use a pump, that's well water. It has nothing to do with the water quality. Daniel Meisler, how bad common city toxins are, e.g. trace amounts of drugs, metals, other contaminants, overall tap versus bottled water. Okay, so your bottled waters can use different filtration technologies. Some may use reverse osmosis, some may use carbon filtration, some just may use a basic filter and disinfection. Generally speaking, the big brands of bottled water spend more money on their filtration and disinfection than the small brands. I've had several customers that I sell to that bottled water that have had to recall water from some of your big box retailers. Some of them had to recall dozens of 18-wheelers full of water because it turns out the water was contaminated. So when you talk about the big companies, people often ask me about Dasani and Aquafina, which is Dasani's Coca-Cola, Aquafina's Pepsi. I believe they're both using reverse osmosis. Both those companies are going to have biologists on staff. They're both going to do a lot of lab testing, because if they do have a microbial outbreak, it's devastating to their brand name. Whereas these little brands that you see, generally speaking, they have less sophisticated equipment. The bottles themselves, I don't believe are healthy. That's a whole other issue. I can't pronounce the name. It says, is 1 quart distilled water, 1 teaspoon baking soda, 1 teaspoon sea salt something you would recommend as a drink to clean the body of foreign elements? Absolutely not. First off, I don't believe in any cleanses, and when you take water and you put in a teaspoon of sea salt, it's going to be extremely salty. I wouldn't be surprised if you end up highly nauseated from that. The baking soda is actually just going to make it slightly alkaline. It's going to raise the pH. It's not going to do anything for your health. It may raise your blood pressure from the high sodium content, though. How do chemicals in water affect flavor perceptions? Why does it happen? Okay, and this is a big one. Chlorine is obvious. Often we can smell chlorine in the water, though most municipalities have moved to something called chloramine, which is basically an ammonium ion, which is NH3, and they've removed one of the hydrogens, and either 1 or 2 hydrogens, and they've put chlorines on there. So you have NH2Cl or NHCl2. So what that does, it makes the chlorine less reactive with the organics in the water. There's a whole class of chemicals that combine with organics that are carcinogenic. So, all right, so let me go back to the question. So the question here is, do chemicals in water affect flavor perceptions? Generally speaking, the chemicals that are carcinogenic and toxic, you can't smell or taste. Occasionally there's some, obviously things like gasoline byproducts, some of the, what we call aromatic compounds might have an odor or a taste to them, but oftentimes these carcinogens are in the parts per million or parts per billion level. You can't see, smell, or taste them. It doesn't mean the water's safe. The only way to tell is to test it in an EPA-approved laboratory. And here's another one, can't pronounce his name. He says, Evian is my favorite. I drink 10 times more water if I have it, pH 7.2. Naturally occurring electrolytes contributing to taste, from snow from the French Alps, and then it has this breakdown. Calcium, 80 milligrams per liter, magnesium 26, potassium 1, bicarbonates 360, sulfates 14, chlorides none, silica 15. Okay, so this is where we get into the hype of bottled water, this whole, Evian from the Swiss Alps, or French Alps. And they'll show a lady, doing the yoga poses, she's in Warrior 2 or whatever, on the yoga mat. It's illegal to make health claims in bottled water. They say that you get about 2% of your mineral intake or less from your drinking water. So making claims as to that you're going to cure a host of diseases with your bottled water is illegal to do. If this individual likes the taste of Evian, so be it. pH 7.2 is about neutral. Naturally occurring electrolytes, this is just the mineral composition of the water. Every water has a naturally occurring electrolytes contributing to the taste. Your LA City water is going to have calcium and magnesium and potassium and bicarbonates as well. Some of the other things he mentioned here, sulfates. Sulfates, some people can be allergic to sulfates. Some wines can be high in sulfates at extreme levels. Usually when we say sulfates are above 250 milligrams per liter, it becomes a problem in that it contributes to loose stools and diarrhea, to be graphic. Silica is basically dissolved glass. It's perfectly fine to drink water with silica in it at the extreme high levels. When we get it to silica above, let's say 80 or 100 parts per million, we often get staining. So I get customers at the extreme. I've got a guy in Napa on 300 acres. He did a 25,000 square foot house. I went up there a bunch of times. Did a whole house RO system because he's got stained glass shower doors that cost $20,000 a piece. And silica basically etches into glass, whereas calcium and magnesium might leave water spots. When silica stains, you can't remove it because it's the same as what the glass is made out of. So silica is really one of those secondary contaminants. We get to the next question here. It's about deuterium. Deuterium in our bodies. Okay, deuterium is a form of hydrogen that's slightly different. It's used in nuclear reactors. It's irrelevant in your drinking water. This guy says, bro, we already quit alcohol. Please don't ruin this for us. Question, how is water or chemical dissolved in it affected by weak magnetic fields or large magnetic body rotating around water? This is one I want to address because back to that whole water quackery. The industry goes through cycles with these magical machines that are supposed to do amazing things. So there's this whole segment in my industry of salt-free water softeners where they wrap magnets around the pipes and they claim that somehow it's softening the water. A lot of times with this quackery, you'll hear them throw around scientific or medical terms to sound convincing. Oh, well, this is different than the other magnets. This is inductive magnetic resonance versus conductive magnetic resonance. Our technology is far more advanced. It's hype. Water is slightly polar. If you were to run your faucet and you put a magnet, if you have water running out the faucet, you put a strong magnet next to it, the flow will curve a little bit. It's slightly attracted to the magnet, but beyond that, wrapping magnets around your pipes isn't going to do anything. Okay, I'd like to generally know if I'm allergic to it because all these years of impeccable self-care, I remain chronically skin diseased in the most bizarre and brutal of ways, and it looks like I've never been bathed in a lifetime. I'm sorry you haven't been bathed in a lifetime, or it looks that way. It doesn't sound good. This is from Starlighting the Path. A lot of people do have allergies to chlorine in the water. A lot of women complain that the chlorine might change the color of their hair. Blonde women say it turns their hair kind of a greenish color. In general, chlorine can be drying to the skin. A lot of people can be sensitive to it. As I mentioned before, chlorine is being phased out in a lot of municipalities because of the DBPs, disinfection byproducts, that form when chlorine combines with other organic compounds in the water. So they're using chloramine. Both of these can be removed with carbon filtration at the whole house level. I do very large carbon tanks. At my house, I have about 60 pounds of carbon in a tank. With chloramine, it's a little more difficult. Chloramine being less reactive, which is why it forms less of those disinfection byproducts, is also more difficult to remove. Okay. We all know reverse osmosis water is best. That said, many renters cannot install under the sink filters. Are you aware of countertop solutions? And they're naming a brand out there. Reverse osmosis isn't the best. People often ask me, what's the best water filter? And I'd like to be tactful. I have my own brand, and I do very little residential these days. Years ago when I started, maybe in 2000, 2001, 02, 03, 04, I had my own brand of reverse osmosis. They were all lab certified. I sold thousands of systems a year. All reverse osmosis systems are going to have a carbon pre-filter because the membranes don't like chlorine. So your carbon's going to remove your dissolved organic compounds, a lot of your chemicals. The RO membrane is going to remove dissolved minerals. Some may be good, some may be bad. So getting back to which filter is the best, it just depends on your water. Some people really like the taste of the mineral content of their water, and we've sent it out to a lab. I get people that have well or spring water, and they love the taste. They are just concerned a little bit about chemicals, fertilizers, that sort of thing, so we'll filter for that. We might check for things like nitrates that are common in fertilizer. Sometimes we'll do something like UV to disinfect, which is basically high intensity sunlight. But reverse osmosis versus carbon filter, there isn't one that's inherently better than the other. Here, easy grundle. I was advised to tap the rural water line coming in for a separate spigot to water the plants because it runs through the water softener and filter because too much salt for the plants. What does the salt content mean for human consumption? Water softeners are what we call a cation exchange, where you have calcium and magnesium, or two hardness minerals, and water softeners can regenerate with either sodium chloride or potassium chloride. And it's ion exchange in the sense that when the water flows through, calcium has a +2 charge, your calcium precipitates out, and 2 sodiums dissolve, or potassium if you use the potassium salt. Depending on your level of hardness, the amount of sodium you're putting in your water may contribute to a high sodium diet. Hardness is usually measured in grains per gallon, with 17.1 parts per million or milligrams per liter being 1 grain of hardness. So if someone has 10 grains, that's 170 milligrams per liter of hardness. If we run that 170 milligram per liter hard water through a water softener, we're going to have 170 milligrams per liter of sodium or potassium in the water when we're done. So we can then take that water and drink it right there, and you have either the high potassium or high sodium in your water, or you can run it through reverse osmosis, which generally is going to remove about 98 or 99% of dissolved minerals. Skip that one. Here's one, messages in water. Someone showing us snowflakes and what they say. And I've heard all kinds of stuff about changing the chemical structure of the water and, you know, the snowflakes and this and that. Water is H2O. There's no way to restructure it. It's 2 hydrogens and an oxygen. Advice on drinking slightly salted water in the morning. I'll leave that up to your doctor as to if you want more sodium in your diet. The truth about water treatment, chlorine, fluoride, etc., effects on health with no BS. This is from Stefano Scalia. Okay, the truth is the municipalities put chlorine in your water because without it we'd have mass disease outbreak. They put enough chlorine in to control microbial growth. If they put enough to sterilize the water, the health effects would be detrimental to everybody. We know that chlorine combines with organics in the water and it forms disinfection byproducts. There's a class of over 100 chemicals. You'll see on your water quality report DBPs, which is an abbreviation, disinfection byproducts, or HAA, which is haloacetic acids. These are all compounds that form in combination with chlorine. And we talk about haloacetic acids, your halogens are chlorine, fluorine, bromine, and iodine. Anytime we have an organic molecule that has one of those, chlorine, fluorine, bromine, or iodine, it's a suspected carcinogen. Not all organic compounds that have those halogens in them are carcinogenic, but many are. The modern world we live in, there's thousands and thousands of chemicals that we deal with every day and we come into contact with. And these chemicals can end up in our water supply, and with many of them, we don't know the effects. You know, we haven't done extensive studies on hundreds of thousands of chemicals. There's the core ones that are on your water quality report, which are required to be tested as part of the EPA Safe Drinking Water Act. There's many that are unknown. For that, carbon filtration and reverse osmosis are usually your best filtration medias. Does RO water leach minerals out of your body? Kevin Wheeler. This is a common question I get, and this is just another one of those hype and quackery issues. RO doesn't leach minerals out of your body. The basis of this, when we have very pure water and we say purity below 20 parts per million, the water can be aggressive and it wants to dissolve minerals. Generally, if we have very pure water, we can't run it through copper pipes. People want to do reverse osmosis for the whole house. I don't recommend it. I've had people do it and they end up having to repipe the house because they have pinhole leaks everywhere. They have blue-green stains in their kitchen sinks, their toilets, their bathtubs, and of course a high copper content in their drinking water. And if there's brass or other lead-containing materials, then with a whole range of other things. And let's address lead while we're here. Houses plumbed pre-mid-1980s when lead was banned across the United States can have lead in the drinking water. Generally speaking, if you have lead in your water, it didn't come from your municipality. It's not going to show up on your drinking water report from the city. If you're renting an apartment or a condo that's very old, there's a chance you have lead in your water. If your house was built pre-mid-1980s, there's a chance you have lead in your water. Okay, so let's get back to the question. Does RO leach minerals out of your body? Absolutely not. As soon as the water comes into contact with all the organic compounds in your mouth, it's gotten up to a state where it's less aggressive. It's dissolved the organics, all the plaque that's on your teeth and on your tongue and your saliva, and by the time it reaches your stomach, the water's neutralized itself as far as that aggressiveness of wanting to dissolve minerals. So no, it's not going to leach minerals out of your body. Okay, so Josh and Jemmy, what are the biggest things to watch out for in their levels? The biggest things to watch out for are going to be your disinfection byproducts. The majority of you are on city water, tap water, and so those are going to be the things that combine with the chlorine. Something as simple as a Brita filter, we'll get some of it. The Brita filter is very small in capacity, and this is once again where a lot of these claims, that you might see these claims of 99% removal, and yeah, it might do that for the first 5 or 10 gallons, but then it's going to fall off very quickly. The larger the carbon filter, the more organic compounds it can remove. So for those of you that are on a city feed and you're most concerned about carcinogens and contaminants, the first thing to start with is a good carbon filter to get rid of your disinfection byproducts and your HAAs, haloacetic acids. Tap water versus spring water, hard water versus soft water, distilled water, salt water, coconut water, ranch water. I covered the tap versus spring water. It's just a matter of, generally speaking, okay, if we want to break it down a little more, your tap water, if it's coming from a river, rivers are generally speaking going to have a lower mineral content. We're more likely to have microbial contamination. There's, once again, with this Evian from the French Alps, and the woman doing her yoga with her, Warrior 2 or whatever pose on, in the commercials. Your spring water is coming from underground. Spring water is closer to the surface. It's more likely to have microbials. Deep well water is going to generally have a higher mineral content. River water, this conception that water was pristine before mankind came along. The bears, the salmon, the trout, the sea otters, they all urinate and defecate in the water. It all needs to be filtered. So you can have coliform bacteria, you can have a whole range of diseases in your surface water, your shallow well water, and in fact even in your deep well water. And it's very common. I get a lot of applications. People are on well water and they have a septic system. Is it possible for them to cross-contaminate? Yes, absolutely. It happens all the time. And the other thing, people do one water test and they think everything's fine. Just because your water tested fine today, you're going to get a totally different profile on well water and even surface water after a big rain. There's a famous philosopher, Heraclides, who said you can't step into the same river twice. The only thing constant in the world is change. So your well water, your surface water are constantly changing in quality and in the contaminants or nutrients that are present. Evolutionary isn't kind of odd for a species that came from the sea long ago and that remains physically majority composed of water, that seawater is not potable for us. It just seems weird when most of the water out there is seawater. Well, yes, but you can't drink seawater. Your body didn't evolve to operate on seawater. And once again, we talked about the kidneys and filtering the blood. Seawater being higher salinity is not going to filter your blood the same, and the salt's going to make you sick. Don't drink seawater. Is it true that mineral water with high mineral levels, San Pellegrino, is significantly better for hydration and muscle growth than tap water or other water? No. Once again, this is one of those water quackery issues. It's illegal to make health claims based on the water. So as far as your vitamins and minerals, take a high quality vitamin and mineral supplement. You're not getting it from your water. I'm using filtered tap water in the last 10 months. Is it true that the water doesn't have minerals being filtered? I was buying mineral waters for many years and don't feel a big difference now. You don't feel a difference because you're getting less than 2% of your minerals from your drinking water. What commercial bottled waters are most appropriate for true hydration? None are better than others. Estrogenics, hormone disruptors found in water supplies and their impacts on health, hormones, fertility, mood, etc. I think this is a big area of discussion, a huge topic. Almost everybody's on some sort of pharmaceuticals these days, whether it's medication for cholesterol or blood pressure. These pharmaceutical byproducts do end up in our water supplies, they end up in our reservoirs, they end up in our groundwater. There's literally thousands of chemicals we're all exposed to. Those do end up in water. Carbon filters are going to get a lot of them, many of them are organic based. Reverse osmosis will likely remove more than just a carbon filter. So back to, if you want to remove the most stuff from your water, reverse osmosis is the way to go. Question here, Scott J. Howard, period ETH. Got period ETH after your name. He doesn't have the laser eyes, but he's .ETH. So Scott says, I've been drinking 1 gallon per day for 55 straight days. I'm pretty sure I'm urinating 1.5 gallons. Minimally, my body hasn't adjusted and I need to pee all the time. Am I saturated or should I be looking at potential issues? Well, if you drank a gallon a day and you peed 1.5 gallons, a gallon of water weighs 8.5 pounds, so you peed out 4.5 pounds a day for 55 days. So it sounds like you lost over 200 pounds in 55 days. Good for you, Scott. You should be on one of those TV shows, The World's Biggest Loser, you know, the weight loss show. You're a candidate. In the garden, the rainwater does magic to plants and they thrive and grow rapidly. Tap water doesn't do much. Would people benefit by drinking rainwater? If yes, how can we gather rainwater, cisterns or tanks? Yes, I have lots of customers in Hawaii, Puerto Rico, other areas that have high levels of rain and they have rain catchment, big tanks. And generally speaking, we run a sediment filter, a UV light. Sometimes we'll do a little bit of a carbon filter. Rainwater can have microbials in it, particularly on the roof. We get a lot of bird droppings in there. So we definitely like to disinfect that water and sediment filter it as well. As far as why your plants do better, rainwater is similar to RO water. The pH is going to be between 6 and 6.5, generally speaking, whereas your tap water is 7.2, which stops your pipes from corroding. Plants generally like lower pH water. It helps dissolve nutrients into the plant stem. So oftentimes, like my customers that do hydroponics, sometimes we'll do acid injection, we'll drop the pH to 6 or 5.5 before we add nutrients. And that could be, I have customers that do hydroponics, of course, with the cannabis growers, and then there's the tomatoes and lettuce and all kinds of fruits and vegetables grown with hydroponics. All hydroponics applications, the plants like a pH below 7, anywhere between 5 and 6, generally speaking, is what people aim for. Switching from premium spring water to Brita has improved my quality. This is a great one, okay? This is a great one from Dalton here. This is the placebo effect in action. Switching to premium spring water from Brita has improved my quality of life substantially, more than I would have anticipated. Any science of that? No, absolutely none at all. Why is water so beneficial? It helps relieve my headache, my back pain, my bloating, UTI, etc. How much water is okay? Water is what's being used to filter your blood. Water is what's removing contaminants from your body. Is filtered refrigerated water as safe as reverse osmosis? I think people are talking about a lot of the refrigerators have these filters built in now. They're a carbon filter. They're not the same as reverse osmosis. Just like any carbon filter, and I'm going to touch on this again and again and again. Whether you're using Brita, you're using one of my countertop filters, whether you have my whole house backwashing carbon tank, whether you have a carbon filter in your refrigerator, the total amount of carbon present, the capacity of the carbon, the amount of contaminants in the water is going to determine the life of the carbon. If you run your carbon too long, it doesn't matter whose system, carbon can oversaturate. I get these people that have a filter they haven't changed in 15 years. You're not doing yourself any sort of service. What happens is carbon's going to hold more when it's cold, and then when it's warm, it's going to release what it absorbed during the winter. So all you're doing, it's like a sponge. You're absorbing more in the winter, and then you're squeezing it out, like squeezing the sponge. In the summer, you're putting it back in the water if you run your carbon too long. Does chlorine as disinfection kill all bacteria? Yes, chlorine will kill all bacteria. Once again, your tap water is chlorinated to control microbial growth. And typically when I have well customers, we'll aim for 1 milligram per liter. A lot of times when I do chemical injection pumps for homeowners or small municipalities, we can't control the chlorine level as precisely. So I like to inject the chlorine, let's say before, let's say a 500-gallon holding tank, and then I'll use an ORP monitor, oxidation reduction potential. ORP is a technique that we can use to measure levels of ozone or chlorine present in drinking water. So we use that to monitor the level. You can disinfect your countertops with a higher level of chlorine. Generally speaking, what I'm going to say is people overdo it with chlorine. You can use, as long as you use unscented bleach, it's fine, but generally speaking, your bleach is 5.25% chlorine by weight. So when we talk parts per million, that's 52,500 parts per million. So your tap water that's chlorinated to 1 part per million, if you used 1 gallon of bleach, you would chlorinate your water. You could chlorinate 52,500 gallons to 1 part per million. Back to Donald Trump with COVID, and he's talking about drinking the bleach. Please don't drink the bleach out of the bottle. You will kill yourself, absolutely. Chlorine's a very strong oxidizer. We might shock chlorinate at 50 or 100 parts per million. As a matter of fact, the law in California and in most states, anytime you do commercial plumbing, that water must be shock chlorinated to 50 parts per million for 4 hours and nothing less. And that's done to sanitize anything that's in the pipes and anything that's in the fixtures. I'm not going to say names, but I get Fortune 500 companies that call me in a panic because they failed county health tests, and they have microbials in the drinking water, in their cooling towers, in their hot water heaters, and all kinds of devices. We had a hospital open in Ohio a few years ago. The pipes hadn't been sanitized with the 50 parts per million for 4 hours. We ended up with Legionnaire's disease. Legionnaire's disease is a disease that can form in water that doesn't necessarily affect you when you drink the water, but when you inhale the water. At the extreme, Legionnaire's disease in big cooling towers can travel in the air a quarter mile away. Back to that formula, 50 parts per million for 4 hours. Anytime you're disinfecting pipes, it's required by law. On commercial buildings, it's not required on residential, and some people will say I'm over the top, and sometimes it can be very difficult to get the chlorine out of your hot water heater. But yes, anytime plumbing work is done at my house, I shock chlorinate the pipes. You do not want to drink 50 part per million water. It's toxic for you. Anything more than 1 part per million, I don't recommend drinking. Ideally, all chlorine should be removed with a carbon filter, but if you're drinking chlorinated water, 1 part per million max, do not drink. So let me get back to the question, okay? Let me start this from the beginning. The best home solution, what filtration tech is best? It's going to depend what's in the water. Dairy, D-A-R-R-R-I. So he says RO plus UV. So yes, I use RO plus UV here. RO is removing the minerals and the dissolved organic compounds. UV is killing the microbials, bacteria, viruses, mold, fungus, yeast, and algae. And then he talks about remineralization. It's up to you. That's a taste preference. I'm not going to, once again, all this hype with these water ionizers. And, I had a friend that's a college friend that used to buy filtration from me. And then he got into all this water quackery stuff. And, he said he wanted live water. He was talking about remineralization. And I said, well, what do you mean you want it live? And he says, well, I want living water. I go, well, you want me to pee in it? You want me to take a dump? I mean, what do you want? Mold, fungus, yeast, algae? You want viruses? There's no such thing as living water. You have your water, and we have our organics and our inorganics. Your inorganics being your minerals that some of these people are calling living water, and then you have your microbials, bacteria, viruses, mold, fungus, yeast, and algae. None of those are essential to have in your water. And then it gets into science behind fringe tech, structured water. There is no science behind it. It's fringe tech, it's hocus pocus, it's water quackery. There is absolutely no science behind structured water. What's the deal with electrically charged water that I see being advertised once in a while? It's hype, hocus pocus. If you were in the bathtub and you dropped the hairdryer, fortunately we have GFI outlets nowadays, but if you electrically charge your water, like you dropped your hairdryer in the bathtub, when you're in your bathtub, you would electrocute yourself. You don't want electricity in your water. You're going to shock yourself. It's not good for you. Are water ionizing machines, so this comes up so many times, are water ionizing machines like Hagen any better? No, that's that water quackery. How much salt do you add to your water? You don't add salt to your water. It's going to give you a high sodium diet. Does drinking bottled distilled water properly hydrate you without the presence of minerals? Once again, taste preference, 2% of your minerals from your drinking water. What are the effects of drinking hard water or showering with hard water? There are no health effects to drinking hard water. The calcium and magnesium are an essential part of your diet, whereas if your water's soft, you've replaced those with potassium or sodium. If you shower in hard water, it can dry your hair and dry your skin, which is why a lot of people like soft water. Also, hard water locks up soap chemically, so most of your soaps have additives to deal with hard water. So when you go to soft water, there's a couple of things that soft water does for you. It does make your skin softer and your hair softer in the showers, less soap for your laundry. Your clothes will last longer and do come out softer when you wash them with soft water. Okay, memory of water. How effective is inverse osmosis process to get clean water? Water doesn't have a memory. This is another water quackery thing. It doesn't remember the contaminants that were in there last week. It's H2O, it's 2 hydrogen and an oxygen. Andrew addresses some questions. Does large amounts of water increase my prolactin levels? I'll leave that to Andrew. And any of the neuroscience and bioscience questions, I'm going to leave to Andrew. The water science stuff I'm going to answer here. I'd love to hear comments on water additives like Mio, Liquid V, Smart, Sparkling Water. Waters with additives have sugar in them. You're adding sugar to your diet. Look at the ingredients. It's like anything else. Are you adding calcium and magnesium, which are essential minerals for your body, or are you sticking sugar in your body? Just like all your other foods. Look at the ingredients. Okay, Philip Berman. I live in Mexico. 99% of our water comes from number 7 plastic, 20-liter bottles. Are there ways to reduce the harm from phthalates we're exposed to? Okay, phthalates, and this is spelled a funny way, Phthalates, and this is an interesting one because phthalates are not regulated on the EPA Safe Drinking Water Act. Many of our pharmaceutical drugs have systems that are made that have phthalates in them. So let me explain what phthalates are. Phthalates are a softening additive that's added to PVC to make it flexible. So a lot of these soda fountain bars that you all are using, when you go to your fast food restaurants and you refill your Coke or Pepsi or Sprite or whatever, that flexible tubing that you're using to fill has phthalates in it. And this is an interesting one that comes up. Okay, so the way to remove it first is not to get it in there in the first place, is one way, is not to use equipment with phthalates. And number 2 is carbon filters and reverse osmosis. But where this gets interesting is that the EPA is not regulating phthalates, but Europe has banned phthalates. So I have a brand of tubing that I sell that's used in a lot of pharmaceutical processes. Well, a few years ago, when phthalates were banned, this was in the last 5 years, okay? Well, Europe banned phthalates, and so this manufacturer that I had, wanting to be ahead of the curve, and because they have a lot of customers in Europe, they switched to a different additive on their flexible PVC tubing that's phthalate-free. So I had a bunch of pharmaceutical companies call me, and they were willing to spend ridiculous money to get that old PVC tubing that had the phthalates in it, because it's incredibly expensive to get a drug FDA approved. It's in millions of dollars. In fact, I have a company I deal with that develops the drug manufacturing process, and they'll use clays and carbons and submicron filters and UV and all kinds of other stuff to remove contaminants from drugs. And once they come up with a manufacturing process, you literally have a bookshelf full of books. And when I supply them with materials, it's who did quality control on the plastic resin, who made the tubing, who did quality control on the tubing, who was doing quality control in the laboratory, who made the ingredients that went into the tubing. So the reason your prescription drugs are so expensive is because we go through such lengthy means to make sure there aren't carcinogens in the end product. And you all see these lawsuits over, when you hear about your cholesterol or whatever medicine, and it turns out that it had these carcinogens in them. This highly expensive FDA-approved manufacturing process is how we prevent these carcinogens from getting in there in the first place. So phthalates is a big one. We're going to see a lot of our drugs have to go through reapproval in the next 5 to 10 years, because as these systems need repairs and this older PVC tubing is failing and they need to replace it, they change that one item, that tubing, to something different. The whole system needs to be revalidated. Here's a good one. Are there microplastics in bottled water? Should you filter bottled water? In what regions is tap water okay to drink? I didn't touch on bottled water yet, and I don't think it's healthy to drink out of plastic. I don't use any plastic to cook. I have glass bottles that I use. In my house, I use reverse osmosis. All plastics leach. Somewhere I have charts, when I do high purity lab water, and there's different grades. There's reagent grade, water for injection, all kinds of stuff. But we have charts that we use in the industry that show the amount of leachables each plastic compound has. So All plastics do leach. If you are going to drink out of plastic, please don't leave your bottles in your car or out in the sun on hot days. High temperatures and sunlight will cause the plastic to degrade more, and you end up with more plastic in your water. And microplastics are a huge concern of mine. I think they're everywhere in the environment. I think they're in our food chain, and it's impossible to get rid of. I cook with stainless steel and glass, and I don't use any plastic anywhere in my kitchen. In fact, I was looking for parts recently. I have a juicer here, and it's a lot of work to make juice. I have this stainless steel juicer, and I looked online, and the thing's like $1,600 now. I think I paid like half of that years ago. And I was looking for something easier that didn't have plastic in it, and then I reminded myself why I bought the juicer that I did. Everything else has plastics, and sure enough, if you have grinding and plastic, you're going to end up with plastic in your food. I want to know your opinion of the EPA pumping contaminated water from East Palestine below the water table. They're probably pumping groundwater because they're afraid that it's seeped in and contaminated the water, and they don't want it to get into Lake Erie. So groundwater hydrology is a whole separate field of study. You know, but I did some groundwater hydrology, and we get into soil porosity, permeability. There's all kinds of variables that could play in: sand, silt, loam. Different soils have different rates that they transmit, and then the pressures in the different underground aquifers. So basically, I'm sure there's a lot of scientists out there, people with educations like me, some groundwater hydrologists, and they'll dig wells and they'll take water samples, and from that they can tell how that plume of contamination is migrating, and they want to get it before it gets to Lake Erie. So that does make sense. I asked, are there benefits to drinking sparkling versus still water? Sparkling water's been carbonated. Carbonation is basically CO2. Pumping CO2 into your water isn't going to affect the health or quality of the water in any way. You might burp a little bit because you're ingesting dissolved gases, but beyond that, there is no health difference between carbonated and non-carbonated water. Here's a good one. I'm going to make this the last question, okay? What amount of dissolved solids for optimal absorption? How much Celtic sea salt should be added to filtered tap water for this? You know, these people keep bringing up this adding salt to your water, and I don't know where this came from. This must be some new trend I've never heard of, but I don't think it's healthy to add salt to your water. As far as optimal TDS level, total dissolved solids, TDS is a term we use for all the dissolved mineral content, and there is no optimal level. Your EPA secondary contaminants are 500 parts per million. Anything above that, the taste is going to be kind of a little bit off-putting. So secondary contaminant, when we talk about the Safe Drinking Water Act, we have our primary contaminants, and those are your carcinogens, your heavy metals, bacteria, viruses, that sort of thing. When we talk about secondary contaminants, that's health and aesthetics. If the water looks a little cloudy, the smell's a little funny, the taste is a little off, these aren't things that are going to injure or kill you, but they're just not pleasant. So when we talk about secondary EPA levels, 500 parts per million is your level for dissolved mineral content. Anything below 20 or 30, we have a risk that it's going to leach metals out of pipes. And generally, your good tasting bottled waters are going to be between 20 and, let's say, 150 or 200 parts per million for what people find is an appealing taste. Beyond that, it's back to what's in there: calcium, magnesium, zinc, good stuff, or bad stuff like arsenic, lead, and mercury. So it's what's in there, not the quantity, that really matters. So I'm going to wrap it up at this, and then I'm going to try and insert a segment. I did another podcast a while back on when I built the world's most energy efficient seawater desalinator, and I did a primer on water treatment technologies there. I'm going to try and insert that here. But this is the end of this podcast on water science. Thank you for listening. I'm Dan Salzberg, your host. My company is bigbrandwater.com, and this is Smart Science. All right, let's do an introduction to water science and water chemistry and filtration, so we can have a good intellectual discussion about how to treat water and how to deal with some of our water shortage issues. So I've got a bunch of filters here in front of me, reverse osmosis membranes. To start with, let's deal with the basics of water chemistry. So when we have water, we have three kinds of contaminants. They're going to be physical, biological, and chemical. So here I've got some Kona brew coffee that I've been ice brewing in the refrigerator here. Along the sides here, you see there's a bunch of coffee grinds up here. That's physical contaminants. So in a municipal tap water feed, whether it's the city feed or the wastewater feed, we can have suspended sand, dirt, sediment, that sort of thing. Then we can have leaves and twigs, other kinds of physical contaminants. And it can get tricky, and the reason I want to use this coffee, with some contaminants, it can be partially dissolved and partially suspended, like this coffee. Some of the coffee is dissolved, some of it's suspended. And so when we get into organic matter, that's very common. When we have plant matter, we might have some leaves in the water, but then we also have dissolved organic tannins that are decaying plant and animal matter as well. All right, so to start with filtration, this would be the coarsest filter here. This is probably about a 20 to 50 micron. This is what we call melt-blown polypropylene. So polypropylene is heated like a liquid, sprayed out of a nozzle. The size of the nozzle, the rate, controls the micron rating. This is just a generic, then we're going to get into my brand here. This is a 0.5 micron absolute. By absolute, we mean it's going to remove 99.98% of the particles at 0.5 microns. All these filters here are what we call DOE, double open-ended. You can see both ends are open. This has a polypropylene core, so it can take differential pressure. So when we put this in the housing and tighten it, we're counting on clamping on the ends to create a positive seal. That works up to a point, but then as we get further into filtration, and we want to do, let's say, food and beverage, biotech, lab, I commonly get called into Fortune 500 food companies and a lot of bottled water companies when they fail their lab tests. They're generally using a filter like this, and really they need to go to something like this. This we call 222 O-ring, so we've got double O-rings on one end. This is going to fit inside a seal, whether it's a polypropylene housing or stainless steel. Often in food and beverage and biotech we use stainless because we like to steam sanitize. It's going to be sealed at the other end. So this is just going to give us a more positive seal. The other difference is we move from the pleated polypro, this is, melt-blown polypropylene. This is pleated polypropylene. Hard to tell in the video here, but there's a lot of very fine pleats in here, so it has a lot of surface area. This is 99.98% at 0.2 microns. Pleated polypropylene is still what we call a depth media, meaning not everything is caught on the surface. There are other ways to filter. This is my brand filter as well. This is called an ultra pleat. This is a 0.2 micron as well, DOE, double open-ended. This material has charged nanofibers on it. These are going to attract organic molecules and other suspended solids based on a chemical charge. So once those particles bond to this, they're not going to wash off. This has unique applications. I've got a lot of customers, whether it be cosmetics, biofuel, all kinds of other applications where they insist that this is working better than a straight mechanical filtration. Then we move further. This is what we call a membrane filter, where it looks very similar to the polypropylene. This is nylon. There's also PES, which is polyether sulfone. Imagine if we had, let's say, like a piece of this saran wrap, and we took a pin and put a bunch of tiny little holes on it, and everything's caught on the surface. So we lose the depth ability, so a lot of times we'll have some of these other filters in front of it to get most of the stuff out. The advantage of something like this is 5 log reduction. So we'll call this cold sterilization. Legally, we don't like to call anything disinfectant unless it's using one of the EPA-approved disinfection technologies, which are going to be commonly chlorine and then ozone and UV, and emergencies iodine. So 5 log reductions means 99.99999%. And while it might sound like, what's the difference in 99.98 and 5 log, when we have bacteria and viruses that are growing in the millions and billions, it does make a big difference. It's one thing when someone wants to filter some water to stick in the refrigerator to drink in a day or two, but if, for example, I had a water store in my last warehouse, this water was bottled in 2012. So this has, actually this one has 99.98%, but then I'm ozonating at a level far beyond what most bottled water uses, and then I use glass bottles. I had reusable bottles, and I ran very high levels of ozone, so someone could take a bottle they've drank out of, rinse it out with the ozonated water, fill it. Ozone's unstable, so it has a 20-minute half-life approximately. So you cap the bottle, and in a few days all the ozone's gone, but the water's sterile. So then as we move further on here, We've got reverse osmosis membranes. There's no difference between reverse osmosis and seawater desalination, and this is one of the first misconceptions about this industry. This is a residential reverse osmosis membrane. The membrane leaf in here is the same as the membrane leaf in this membrane here. And the way these work, there's a tube in the middle with a bunch of holes in it. Then we have attached membrane and then a layer of netting, and it's wrapped like a roll of paper towels. If you look on the end, it's what we call spiral wound. So the water is going to work its way through that membrane leaf down to that center with the holes and then out the end. The difference between, let's say this home reverse osmosis, this is going to operate at, let's say 60 or 70 psi. This is what we call a low pressure reverse osmosis membrane here. This is probably 100 psi. And this is what most of the municipal plants now that are recycling wastewater are going to use something like this. I just supplied Orange County with some membranes for a pilot study. They're the leader in recycled water in the United States. They're recycling 100 million gallons a day. They want to expand to 120 million gallons a day. It's very common. You know, my company's not large enough. I don't have huge cranes and tractors and do the big construction to build a municipal water plant. But before they build the plant, they do a study and they want to see that it's going to work before they spend that money. So often I'll build those pilot studies. So this is our residential membrane. This is our commercial membrane. They'll typically go into housings like this. This is fiberglass, FRP we'll call it. You'll see on the end here there's two fittings. It almost looks like they're both off to the side. This one's actually catching the water in the center, this off to the side. So the water that comes down the center we'll call the product water, the side is the wastewater. That's what's commonly used in water. Within the industry we call it permeate and reject, because the water coming out the center isn't necessarily the product. For example, I have a lot of customers that make maple syrup. So what we do is we're going to try and run like 80% recovery. So the water coming out the center is the water, and then the maple syrup is coming out the side. That's then the product. So permeate and brine is what we'll call it in a commercial application, or product and waste when we talk about water. It's very common to have multiple membranes. We'll have very long housings. This is a standard size, 4 by 40, 4-inch diameter, 40-inch long. We also have 8-inch diameter, 40-inch long. So we get into the big municipal plants that are recycling wastewater or municipal reverse osmosis or seawater desalination. You'll have a whole bunch of 8-inch by 40-inch membranes. A typical housing is going to hold 6 membranes. So the snouts of each membrane will lock together. And we'll take the waste from the first set of membranes. That'll be the feed to the second set, and then the waste from the second set feeds the third set. Generally a triple array, so that we're able to get maybe 80 or 82% recovery when we deal with regular tap water or municipal wastewater. And this is one of the areas where, when we talk about seawater desalination, and I talk about how grossly inefficient it is, there's a couple of variables going on. One is that in seawater, it's rare that we're going to get over 30% recovery. So we're going to have to pump this water at 1,000 psi, and only 30% or about 1/3 of it is going to be product water. Whereas when we recycle municipal wastewater with a membrane like this, we're going to pump it at 100 psi, much less pressure, and 80% of that water is now the product water that's reusable. So a huge difference there. There are some subtleties when we do seawater desalination. We use energy recovery turbines, so generally we're running 600 psi, and then because that wastewater is coming out twice as fast as the product, we have essentially, we call it an energy recovery turbine. It's like a turbocharger. So we have that wastewater shooting through there, it's spinning a turbine, and that's taking that 600 psi feed and bumping the pressure up to 1,000 psi. So then the difference between this membrane and seawater desal is going to be the seawater membrane is going to have a fiberglass wrap. The membrane, we'll talk about looseness or tightness. So this is a very loose tap water membrane, 100 psi. A tighter tap water membrane would maybe be 200 psi, and then seawater about 1,000 psi. And there's a whole bunch of stuff in the middle, and this is an area where there's a lot of misconceptions. Like online it'll say California has 12 desal plants. It has one plant, the one in Carlsbad. The others are brackish water. So when we talk about, there's a term TDS, total dissolved solids, which is the total mineral content in the water. And it doesn't matter, it could be calcium, magnesium, sodium chloride, whatever it is. It's mineral content. Generally, your tap water is below 500 ppm. We'll call anything up to 2,000 ppm tap water. Between 2,000 and maybe 20,000 or 25,000 we call brackish water, which is somewhere in the middle. And then above that we call seawater. Typically seawater is about 35,000 ppm. And this is the core of the challenge with seawater desalination. And you know, there's loads of engineers in this business. The membrane industry is a multi-billion dollar industry. There's a lot of engineers that are working on new membrane technology. And each year they get a little bit better, maybe as far as reduced fouling and that sort of thing. But the one thing we can't overcome is what we call osmotic pressure. And in rough terms, for every 100 parts per million of the TDS, that total dissolved solids, there's 1 psi of osmotic pressure. That's back pressure on the membrane. So in a nutshell, if we have 35,000 ppm seawater, it actually works out to about 400 psi of osmotic pressure. So if we have a seawater membrane, let's say we have this housing, we have a membrane in here, and we pump the water in here at 400 psi, we're going to get 0 out with seawater, whereas if we had brackish water or tap water, we would get a lot of product water coming out the end. So the big challenge when we deal with seawater desalination is the high pressures we have to deal with, and then aside from that, there's the corrosion issue. Seawater is the absolute most corrosive liquid known in the world. It's more corrosive than lacquer thinner or paint thinner or acetone. Regular water will dissolve a lot of things, but salt water dissolves pretty much everything. So when we do seawater desalination, aside from the high pressures, we're dealing with some exotic stainless steel alloys. Regular 316 stainless, that the chlorides will pit it and destroy it in a few years. So we use specialized materials. So that's kind of the basics of filtration. There's some stuff in the middle. This is nanofiltration. We'll call this sometimes a softening membrane, but this is going to take out a lot of the dissolved minerals, mostly the ones that have a 2 or larger charge. Some of the +1 or -1 charged dissolved minerals are going to stay in the water. This is commonly used in beverages. And right in the middle, there's something called UF that's between this 0.25 log and nanofiltration. We have UF, ultrafiltration, and this is the hot thing now. Every new municipal plant gets an ultrafiltration system before the water gets chlorinated, and that's going to remove a lot of the very fine suspended solids. UF is 0.001 microns, so about 1,000th of a micron. And just in reference, a human hair is 60 to 80 microns thick. Generally, in a drip irrigation or a sprinkler system, we're going to filter to about 50 or 60 microns. So when we get down to 1,000th of a micron, in perspective, everybody's talking about COVID right now. Generally, at the 0.2, we're getting most bacteria, most viruses, because they tend not to free float in water. But viruses can go as small as, I think, 0.03 or 0.02. So that UF membrane at 0.001 is even getting viruses out. It's going to be a little different than this. That's usually what we call a capillary tube membrane. So it might be a tube like this, but inside, instead of it being spiral wound, we'll have a bunch of tiny little tubes that look like straws in there, and the water might start in the middle and work its way to the outside of the straws, and then we back flush those. So a membrane like that, in a UF application, whether it's municipal feed or also the municipal wastewater, we use that, and we'll talk about that when we get into recycling. We might run that membrane for a day or two, then we're going to backwash it for a couple minutes, and the backwash is going to be loaded with suspended solids, which we can then put off into a pond and let it evaporate. So this is kind of the basics of filtration. The only other thing I want to throw in here is pH. There's a lot of misconceptions about pH in my industry. There's a lot of what we call water quackery and hocus pocus. You'll see a lot of these countertop water systems, they call them ionizers, and they talk about alkaline water. Alkaline versus acid has to do with pH. pH is the negative log of the hydronium ion. And what that comes down to is you have a certain amount of hydronium and hydroxide at all times dissolved in the water. Hydronium is H+, hydroxide is OH-. So you have a whole bunch of water molecules that are disassociated from H2O to this H+ and OH- kind of floating around in there. So with a pH of 7, there's an equal level. When we go to a pH of 6, there's 10 times more H+ and 10 times less OH-. pH 5, it's now 100 times versus the pH 7. So all these systems that are claiming that they cure all these diseases, it's a miracle. We do pH adjustment at the municipal level all the time. In reverse osmosis, it's very common. We might inject acids because the big problem we have is mineral scaling on the membrane. So if we drop the pH from 7 down to maybe 6.5 or 6 or even 5.5, we might be able to recover 85% or 87% instead of 75 or 80%. So we'll do things like pH injection, also some anti-scaling chemicals, because we are so concerned about the energy consumption with any of these membrane systems. All right, so this covers the basics of filtration. The only other thing I have in here, this is a carbon filter. This is a pulverized carbon block, another one of my brand. When we talk about dissolved organics, we talked about those suspended dirts and clays and that sort of thing. When they get dissolved, carbon filters are used to remove it. Sometimes we use ozone to decompose it. So we can decompose a lot of that decaying plant and animal matter back into carbon dioxide and water. We can filter out the nanofiltration and the reverse osmosis. Generally tend to reject most of those dissolved organics as well. The one thing I want to leave you with here, I've had several companies come to me. I've had Fortune 500s come to me, and they'll say they have a metal plating or a grinding operation. So after the grinding, they have a jar like this. They've got metal grindings. Okay, they take this water and they feed it back into the RO system. And the other side, we've got product and waste. Once again, we use the product to flush their metals. That goes back in this stream, and they keep recycling it. And this is what we call an infinite loop, where they want to just keep reusing it and reusing it. And they call me scratching their heads, and they can't figure out why they keep ruining membranes. The one thing, if you forget everything else from this, the one thing I want to stick for you to keep in your head is that this is a separation technology. It's not a filter. You hear people call it a reverse osmosis filter. It's separating. Nothing is kept within the filter. One side we have the pure water. Everything that went into that membrane, whether it's these coffee grinds, the organics, whatever, that's going to be in our brine stream. One way or another, you can't create or destroy matter. It all has to go somewhere. Now, when we talk about the ozone and that sort of thing, we can decompose things from a complex organic molecule back to basic carbon dioxide and water, but those atoms are still there. The matter still has to go somewhere. And this is one of the big misconceptions. I mean, I get these guys, they go, I don't know, I thought your RO system was removing it. I'm like, okay, well, where's it going to go? It has to go somewhere. So here it is right here. That's the introduction to water science.